The purpose of this video, this is the fifth lecture of Unit 10, is we're going to try to derive the period formula for two different oscillators. One is the mass on a spring and the other is a simple pendulum. Here we have an object that I think it's apparent is moving periodically, or it's oscillating back and forth. It's going over the same path in a predictable fashion, and it appears to be taking the same amount of time, except for the lag and the jiff, but whatever. Because there's no friction on this system, I can ask this question. Is the object, this mass, exhibiting simple harmonic motion? And we're going to make one assumption that doesn't get stated here explicitly, which is that the mass of the actual spring is negligible compared to the disk that's oscillating on its end. So, how do we know if something exhibits simple harmonic motion? Well, your book has a good definition on page 394. It says, the acceleration of the particle is proportional to the displacement, but in the opposite direction. You could also relate the displacement to not the acceleration, but the force. Remember, force is equal to mass times acceleration. So the same could be said, if the displacement is one way, say left, just for an example, the acceleration and the net force would both be the other way. If that's the case, and acceleration and force both increase as displacement increases, then you have a simple harmonic oscillator. Well, let's see if that's true here. Again, no friction, so the only force acting parallel to the motion, or in the horizontal dimension here, is going to be the spring force given by Hooke's law to be negative kx. I can rewrite this using the differential form of the acceleration, second order differential, the second derivative of position that gives us acceleration. This is actually one of the AP course description objectives. If you can recognize that this necessarily must be a simple harmonic oscillator, then you've met the objective. Why is that? Because on one side of the equation you have position, on the other side you have the second derivative of position, and one of them is negative. Whenever that's true, no matter what these constants are, in this case k and m, you have a simple harmonic oscillator. So the answer here is yes, and one note I want to make, if there had been friction, this would not be in the true sense exhibiting simple harmonic motion. The reason is that we would then call it damped harmonic motion, which is something we'll do in another video. Take a look at that same thing. So what I want to ask is, how could you calculate a few quantities? If I asked you to find the amplitude, or the period, or the frequency, well, we know period and frequency are just inverses of each other, right? If you know one, you just do 1 over it to get the other. T equals 1 over f. Amplitude you could also get pretty easily here, because it's just the distance from equilibrium. So the equilibrium position, I'll look at amplitude first, would be the natural resting place of the spring block system. So where would it be if it sort of wasn't pushed and made to oscillate? Where would it rest naturally? And that's in the center of the motion. The amplitude is then the farthest distance it ever achieves from that, and that's achieved once in the negative direction and once in the positive direction. There's your positive, or x max. There's your negative, or x min. And because those are the greatest displacement, we'll call them both amplitude. Let's think about how would you calculate the period here. Well, for starters, what factors do you suppose might change the period of a mass on a spring? One thing might be the amount of mass that we have going back and forth, maybe the constant in the spring, maybe the velocity of the system, maybe the amplitude or the starting position of the system, maybe something else that we haven't mentioned here. So what I want to do is show you how to derive the formula for the period of a mass on a spring, and then you'll know, 1, what the formula is, and 2, what things do and do not impact its period. So going back to Newton's second law here, where Hooke's law, the negative kx, is the only force, so it is the sum of forces, and that equals mass times acceleration. I want to rearrange this. First, we'll just solve it for A, and that's all I've done here is just a little bit of algebra. And then if I want to make this an equation for the maximum acceleration, that would occur when the displacement is also maximized. And since x max is known as the amplitude, or capital A, you could also write this as A max equals negative k over m times A, where k is the spring constant and m is the mass of the system. Now the reason I chose to do this, to solve it for A max, is because we already have another expression for A max. We derived it in video number 3 or 4, I forgot which one, and then we used it. So you've seen it before, and now we have two different expressions for A max, which means they must be equal to each other as well. So here's the first of those two equations. We just derived it. The other one I'll bring back from the video in the past that we looked at and derived, and it was negative omega squared A So those must be equivalent, and I've tried to color code it so you see what I'm doing here. So A max is on the left side of both equations, and amplitude is on the right side. So that means these blue things must be equal. So let's just set them equal here. And because omega is related to period, using 2 pi over t, I can now solve the period of a pendulum. One thing before I go and finish the math here, look what happened. Look what happened. Essentially what I did was I said A max equal to A max, and then the A canceled out. That tells us something physical, not only mathematical. It tells us that the period of a mass on a spring is independent of its amplitude, which is really not what you might expect. But any conceivable amplitude would produce the same period as long as K and M are the same. Now we can finish it. So I'm going to replace omega with 2 pi over t. That whole thing gets squared. So it's 2 pi squared. That becomes 4 pi squared over t squared. Okay. Let's just get rid of the fractions, multiply both sides by t squared and by m. That gives us this. Divide both sides by k to get t squared by itself. And finally, we take a root. Before I do that, notice what's going to happen here. So the square root of 4 pi squared, I mean, we started this with 2 pi. The reason we have 4 pi squared is that we already squared the 2 pi. So this is just going to turn back into 2 pi. But then we do have a square root of mass over spring constant. This is the final answer. This is the formula for the period of a mass on a spring. 2 notes about it. Like I said before, the period of a mass oscillating on a spring is independent of its amplitude. It depends on the mass and the spring constant only. Velocity, like I said, amplitude, every other factor you may have considered is irrelevant. All we care about is mass and spring constant. And finally, we're going to try to talk about the pendulum once again. And we're going to do this in order to derive a formula for its period as well. So this is the slide you may remember back from the very first video where we showed the different positions of a pendulum all at once. I want to ask this question: does the pendulum exhibit simple harmonic motion? Once again, the characteristic of simple harmonic motion is that the acceleration has to be proportional to the displacement, but in the opposite direction. So in other words, if you push something right, it's accelerating left and vice versa. Well, in order to determine the acceleration of something, we're going to have to talk about the forces. So let's just look at some of these forces. We've got tension forces, those are always present, and we've got gravitational forces that are always present. And you'll notice that the tension forces change in magnitude as the pendulum swings. And that makes sense from what we know about circular motion and energy conservation. Here at the top, assuming we start at rest, all of the energy is gravitational potential energy. At the bottom, assuming we take this to be our y equals 0 point, all of the energy is kinetic. So it's going to have more speed at the bottom. I mean, really, that has nothing to do with where I choose to set y equals 0, but it's just a fact that as you go down, you get faster. We all know that. And if you're going faster, you need more centripetal force to make the turn, and therefore the tension has to be maximized at the bottom. And so this looks like we're onto something. Does any force here increase in magnitude as the bob is farther and farther from equilibrium? Actually, tension doesn't. Tension decreases. Remember that equilibrium for a simple harmonic oscillator, well, not just an oscillator, but for a pendulum, is down the center, right? This is equilibrium for a pendulum. And at this moment, tension is maximized, whereas we're looking for something that has a minimum force, and therefore minimum acceleration at equilibrium, and a maximum force and maximum acceleration at either amplitude. So tension is not the answer. And gravity, it would seem, couldn't be the answer because gravitational force is constant. I mean, assuming pretty reasonably that the mass of the bob isn't changing. So what's going on? Is the gravitational force somehow acting as the restoring force? It is. It is. And the reason is that its magnitude may not change, but as you swing from the center outwards, the tangential component of gravity increases. So to sort of see this clearly, imagine what's going on at the bottom. The gravitational force is entirely anti-centripetal, or away from the center, or sometimes we say centrifugal. Whereas if this were to swing all the way up to where the bob was horizontal, made a horizontal line here, the gravitational force would be entirely tangential, and specifically against the motion. So as the displacement from equilibrium, this angle increases, the component of gravity opposing the motion also increases. So pendula do exhibit simple harmonic motion, and the gravitation is the restoring force. Before I can write a differential equation like we did for the mass on a spring, we're going to have to first figure out what is the expression for the component of gravity that acts as the restoring force, which is the tangential component. So let's just bring back those forces. We have a tension, which acts centripetally, and we have a gravitational force, which has components because, remember, we don't use a traditional xy axis, we use a tangential radial axis. And that means that at any moment in time, the tension only points towards the center, or radially, but the gravitation has an increasingly large component acting against the motion. So let's show those components for gravitation. One radial, that's this side here, and one tangential, that's this side here. And you can see that the radial component is anti-centripetal, or against the center, away from the center, and the tangential component is anti-parallel, meaning against the motion, and that causes the speed to slow down. So let's try to figure out what these two components are in terms of the angle at the top, theta. A little bit of geometry will easily prove that this theta is the same as this theta. Feel free to pause and try to figure out where that came from, but I'm not going to walk through the geometry, and this isn't really that hard of a geometry question. And if you just do some trigonometry here, you get mg cosine theta as the radial component and mg sine theta as the tangential component. Therefore, the restoring force on a pendulum is given by mg sine theta, the tangential component of gravity. Okay, now we can write this differential expression from Newton's second law. I'm going to replace sum of forces with the tangential component of gravity we just derived. And the problem we have is that we have theta on the left side, or the angular displacement, and then x on the right side, or the linear displacement. So let's try to find an expression that allows us to replace x with theta so that we have theta on both sides. That is something we learned in Unit 6 for the first time, which is x equals r theta. Remember, there was this sort of family of equations that allowed you to go from translation to rotation. Like there was also v equals r omega, and a equals r alpha, and all that. So that's all this is. And r is the length of the string, so I'm going to say L. So that's the radius of the circle, or the length of the string in this case. And I'm going to now replace in the numerator of this differential, where it says x, I'm just going to plug in L theta. And because L is a constant, I am going to divide both sides by L. You'll notice I also canceled out my m's in this step. But let's divide both sides by L, giving us negative g over L sine theta equals the second derivative of theta with respect to time. Now we've got a problem. The problem is this: if you don't recognize it, we have sine of theta on the left side and we have theta on the right side. This is not a true differential equation in the sense that we need it to be. I mean, I'm sure this is probably solvable in some way. I don't really know how to solve this, but we can still solve it using our old techniques because we're going to make an assumption here. The assumption is that for small oscillations, say 10 degrees from equilibrium or less, theta is equal to sine of theta. And the book has a pretty good explanation of why we make this assumption and why it's valid. Begins on page 402, chapter 13, section 4. So feel free to check that out if you're interested in why we just did this and also why it's mathematically valid. Okay, so that means I'm going to replace the left side where it said sine theta with just theta. And now I have a true second order differential, right? This is theta and this is the second derivative of theta. So that allows me to finish the problem now. So this again is the equation for the position the pendulum is a function of time, and it should look really familiar. It's the same basic structure as the old equation for the position of any simple harmonic oscillator. The only difference is that theta would be your angular displacement, not your linear displacement. So just like the old formula, the maximum angular acceleration, remember we had that equation for A max, it's still going to be negative omega squared A, where the amplitude of the pendulum, or its maximum displacement from equilibrium, is measured angularly. So it's theta max, not x max. So the maximum angular displacement goes in for capital A here. Why do I do that? Same setup as when we derived the equation for the period of a mass on a spring. I now have two different equations for A max, for maximum acceleration. So going back to this equation from the last slide, and we can say that the maximum acceleration again is the expression on the right, is equal to the second derivative of position when position is maximized. Remember, I can't reiterate this enough. When is acceleration maximized for a simple harmonic oscillator? It's when the displacement from equilibrium is maximized, but their directions are always opposite. That's what this negative sign is for. So we can do the same thing as before. Negative omega squared is equal to negative g over L. These two blue things just got set equal to each other. Negative signs cancel. Omega is 2 pi over t, which is the period. Squaring both the numerator and the denominator gives us this expression, multiplying both sides now by L and t squared. Oh, hey, there's a title. That should not have come in this late, but whatever. That gives us gt squared equals 4 pi squared L. And now just divide both sides by g to get t squared alone and isolate t by rooting it. And boom. This is the formula for the period of a simple pendulum. What does it mean? It means that the period of a pendulum depends on its length, L, and on the acceleration due to gravity, and nothing else. Oscillation does not depend on its amplitude, doesn't depend on the mass at the bottom or any other factor. So one thing to kind of make very clear. For a pendulum, mass doesn't matter. But for a mass on a spring, mass is a factor that influences period. Remember the old formula, the first one we derived, it basically looked the same. It's just what's under the radical that changed. It was the square root of mass over the spring constant. So that is important because one of the two periods does depend on mass and the other one doesn't. Here we only care about L and G.